So, we discussed in previous lectures mostly about the geological structure, and we stopped somewhere talking about the active fault traces and how they are important in our day to day life and for the society as well as for the urban uh, uh, civilization, or maybe you can say the infrastructure development. Now, this is the area where probably I have shown a couple of slides, but to get connected with, I will just quickly talk about this and how different the same data can be used to generate different type of maps. Okay. Now, this is the area which is around between Chandigarh and Pathankot, which is again marking an active tectonic zone, and this anticline which is traversing almost along the frontal part for more than 100 kilometers in northwest Himalaya is known as Janavri anticline. I have discussed this in the previous lectures also. Okay. Now, based on the photo interpretations, again we used high resolution satellite data, which I have been telling you that we are using Cartosat data here, but with the stereo vision capabilities, ortho rectified photographs, we marked the active fault traces in this region. Okay. Now, in one of my slide, probably it is next in couple of slides it will come. Just make a note that this data which we are showing right now is the recent data. Recent data means taken in last couple of years, but the data which we took and used for our studies, okay, which were been collected by US spy satellite long back in 60s, okay, and 70s, that will not show you the existence of this Bias dam, because this Bias dam came later on, and then whatever the hydropower stations were been put on the low lying areas to generate the electricity as well as to facilitate the irrigation in the plains of Punjab, that is Indo-Gangetic plain. The canal was been constructed, and this I mentioned in the past also that this canal was been constructed without having understanding of where active faults are. Okay. And as we have discussed in the past, that what is the importance of active fault and why we need to identify that, I think you understand that portion. Okay. So, these are the fault traces, and the bars which are been marked here or the comms are indicative that this area is low, this is high, and compared to this relatively this is low and this is high, and this side is low, this is high. Okay. So, this comms are indicative that which side is the downside, okay, which is also again very important. So, even I have shown in the in previous slides where we were talking about that you can generate a shaded relief map, and that shaded relief map can give you the topography of this area. Okay. So, this is important. Now, let us go into the detail of this one very quickly and then talk about, okay, that what exactly. So, this is what I was talking about, that you can use the data which is high resolution satellite data to generate different type of illustrations or maps. Okay. So, this again it shows the different elevations, and if you clearly look at this part which I was showing in the previous slide, which we have marked the lines with comms are the active faults, which that is the faults which have displaced the young alluvial plains actually, or flood plain of Bias river, because this is the outlet of the Bias which goes like this, okay, and which is marked by here. So, Bias flows right now like this, and this portion is an uplifted portion. So, this forms a part of the Bias floodplain. Another representations which you can do is you can generate the DM from using the after and forward image of the given satellite data, and this is the area of Pathankot. Now, what beautiful things we can extract out of this is that you can easily extract the drainage. Okay. So, even SRTM data you can use, but SRTM data this is having better resolution than the SRTM data. So, you can easily demarcate the landforms as well as the drainage divides and the drainage network out of this. Okay. This is an anaglyph which I have we will try to provide you if possible, because these are all restricted photographs. So, we will see if we can share with you this anaglyph where you can see all this area in 3 dimension. Okay. So, this whole area you will be able to understand and see that how we have picked up the different landforms and all that. But one thing again clearly it shows here the path of the your canal which was been constructed without knowing that the fault passes through here. Okay. So, fault passes here like this, another fault is over here, and third is over here. Okay. So, where relatively this side is down and here this side is down here. Okay. And then you have this side, sorry, this is the opposite. Okay. So, you have this side down. Okay. Now, this without knowing, because that this area is the topography which they see in this area is because of the active fault or the displacement along the active fault. Unknowingly they have put this hydropower station, and this comparison I did in my previous lectures with the old structure, okay, ancient structure which was been constructed on Pinjore Garden fault by Mughals in 17th century. Okay. Now, if you look at this is another way of generating the contour map you can use. Okay. The same data was been used to generate the contour maps also, and then also the shaded relief map. Okay. So, this is what we were talking about. This is an old photograph which was collected by US spy satellite in 60s and 70s, and this doesn't show the existence of the canal as well as the dam here. Okay. The Bias dam came after this, but this faults existed before that. Okay. So, that there was an oversight, or maybe the people or the scientists were not able to pick up those faults. Okay. So, these are the 2 hydropower stations which have been put on exactly on the active fault. The active fault runs here, and this is the trace of the active fault, as another trace is over here which goes. So, you have a very clear boundary, because this side is up, this is up, I am talking about relative, and this side is down and this is down. Okay. So, relative to this is up actually. Okay. So, if you take in profile like this, and this side is another fault which goes like this here very clearly. So, this side is down. Okay. So, what if you take the topographic the cross section here between, for example, A to B, then what you will be able to see is something like this. So, Indo-Gangetic plain comes like that, then this goes up, then there is another up here, and then this goes down here like this. Okay. So, subsurface what we do is we understand the deformation pattern, and we also understood this or established this based on the trenching which we crossed did across the this area, like for in the at this location, and then we did 2 trenches on this location as well as one we did here somewhere. So, that shows us that the fault is dipping like this. Okay. And this is opposite dipping, and this connect like that. Okay, fine. So, these are all thrust faults, and what we see on the surface is your fault scarps. Okay. So, these are 2 hydropower stations which are put exactly on that. Okay. And this again is not a good selection of site. Okay. So, terrain evolution is extremely important when you are going ahead with such projects. Okay. So, these are the photographs of ground photographs of hydropower stations which have been put on the active fault, and one of the hydropower station, if you see on high resolution Google Earth image, has been shown here. This is the same hydropower station. Now, we also picked up some very interesting information using Landsat data. Okay. So, this resolution is around almost like 28 to 29 meters, but then also the tonal variations. This image is your false color composite. So, you can play with different bands and try to enhance the features, okay, if, as per your requirement. Okay. But for us this was the best, and which gave us an indication that this is a present channel here. Okay. But this present channel, this is again very not very old data, because you see the Bias Dam here and the canal here. Okay. So, this is a present day channel, but what we found was the channel which is coming from here, this is in Pathankot area, has almost like swinged couple of time. Okay. So, one is this is one trace which goes, another trace here and third trace here. So, this also indicate that the drainages or the drainage in Himalayas or flowing on the floodplains are having tendency to shift. Okay. That is one. Now, this shift is a natural shift because of the fluctuation in the velocity or the bed load supply, or what we can say the water carrying capacity is less, or maybe because of several reasons. Okay. Or it is purely because of the tectonic moment. Okay. But since we have a very good example here of Bias getting shifted to its present path, okay, where earlier it flowed through this, okay, and then slowly it got shifted over here, and then finally you are having what you see flowing here. Okay, fine. So, this shift, we understand that this is a major factor which affected this was your tectonic deformation. Okay. So, structural elements, geological structures played an important role for this shift. Okay. Might be some climatic fluctuation, because you can ask the question that this is one of the mighty river which was flowing on the Indo-Gangetic plain, why it was unable to cross hardly a 10 to 15 meter high warp which was developed by the ongoing deformation. Okay. So, of course, that is a big question. It can erode and it can flow through, but the carrying capacity or the river was not capable enough to cross this 10 to 15 meter high landform, okay, which was eventually developed by the tectonic movement. So, the climate was the main factor for not allowing the river to erode this feature and moving ahead. Okay. And finally, it got deflected. So, there are the interpretations which one can make in a different way also. Okay. So, this is the close up of that notch which like this place, and the next field photograph is from here, the Pathankot, where there is a very sharp turn of the channel, okay, where the river comes and flows here. This is a Chakki river, it takes a very sharp turn here. Okay. So, this is again because of the tectonic movement. So, this you can see, this photograph is taken from this side here, viewing this area, which shows the very sharp turn from here and flowing in this direction. Okay. There is again close up of that. So, you have the exit. So, river comes, flows through here and then take almost 90-degree turn here, and this is because of the fault Himalayan frontal thrust movement. Okay. Now, overall whatever we have discussed until now about the active faults, folds and all that, okay, where exactly we can put that what is the implication of that, how we can use this data, and why we are so much keen in understanding all this, okay, or knowing, having awareness about this. Okay. We cannot stop the deformation, ongoing deformation, cannot minimize it, okay, but what best we cannot even stop it. Okay. but what best we can do it, we can minimize the hazard level. Okay. So, what happens during such like events, okay, because the any movement which is taking place on this faults, okay, or the structures will result into the ground acceleration, and that is what we call earthquakes. Okay. So, sudden release of energy which is stored. Okay. So, when we understand, we have been talking about that the Himalaya is getting folded, or and day by day because of the tectonic movements or the collision between the Indian plate and the Eurasian plate. So, this energy is getting stored, okay, but at some point of time it will be released, and those will be released along the active fault lines. Okay. So, the point is that how far we are sitting from those sources. Okay. So, earthquake sources, that is very important, and that what we have been identifying in Himalayas and in other seismically active regions in India, like in Kutch and Andaman. Okay. So, the amplification of the seismic waves will vary from place to place depending on the subsurface geology. Okay. And that is what we call lithology. So, lithological variation will be again an important factor for site evaluation. Okay. Because you cannot have the same type of buildings or design on, for example, the hard rocks or the softer rocks or the softer material, that is what we call alluvium, or the finer materials which we can say that it is comprising of silt and mud. So, the amplification will vary from place to place depending on the site and depending on the lithology. So, the next topic which we are going to talk about, that how best we can identify the lithological variation using the satellite data, that we are going to talk about, and where we will talk about the igneous, metamorphic, sedimentary terrains, how we can see, and how what landforms we can look at, which will help us in identifying the subsurface geology. Now, here if you see carefully this figure, it shows the ground acceleration varies from left to right, and that is because of the change in the lithology. So, in hard rock, the ground acceleration triggered by the same magnitude earthquake will be very less, but as you move into the softer rocks, that are sedimentary rocks, you will have slightly higher, but if you get into the alluvium, again the loose material, you will be having much higher, and in the finer material you will have much higher. Okay. So, this will affect the buildings. Okay. So, even if you say that, okay, I am sitting away from the fault line, of course, the fault line should not be used to go for the construction, but if you are sitting away and on different material, okay, then you will have to take care of that, how best you can construct the houses or the buildings or the structures to withstand that amount of shaking. Okay. So, this is the main important point of overall what we were talking about. The site evaluation is very much important. Okay. So, this is what we were discussing, that if we are having the houses sitting right on the fault scarp and away from the fault scarp, what will happen. So, please recall this figure again. So, if for example, if you are having the hard rocks, we consider this the topography as your Himalaya, and then we have the alluvium coming in, which we talk about, like what we consider the Indo-Gangetic plain. So, what exactly will happen in the Indo-Gangetic plain, you can imagine, considering the amplification factor here. Okay. Fine. So, even if you are sitting maybe almost like 250 kilometers from the fault line, and depending on the magnitude, if you are having larger magnitude above 7.5 or around 8, where we have been talking about that the Himalaya can produce or capable in producing the magnitude of 8.1, 8.2, then the effect will be seen or experienced then covering a larger area. Okay. So, depending on that, sometimes we feel that no, we are sitting away from the active fault, and in previous slides we have seen that active faults are, of course, we need to avoid those locations, but sometimes we say that no, we are sitting away from the active fault, but then also if that active fault is capable of triggering or sourcing the large magnitude earthquake greater than 7.5 or so, okay, then the larger area, maybe up to 350 kilometers in that circumference, will get affected. Okay. So, we will and most populated, okay, as compared to the hilly terrains, like if you take in Himalayas and all that, more population is in the Indo-Gangetic plain. Okay. And we keep on having more buildings and structures coming up in the last couple of years. Okay. As I was talking about that, we are having an infrastructure boom. So, we are right and left, we are having the constructions. Now, whether those sources have been taken into consideration, okay, this is extremely important. And then you may say that, okay, 2015 earthquake of in Nepal, that is Gorkha earthquake, did not result into much damage in the Indo-Gangetic plain, but if you think so, that okay, let us consider that the earthquake which was triggered in like Gorkha earthquake was almost like 100 or 100 kilometers south of or north of the Himalayan front. Okay. So, I will just put in sketch. Okay, this is an Himalayan front here. So, earthquake epicenter was somewhere here, but now if I move the earthquake epicenter here, then the effect in this area will be different. Okay. So, that is an Indo-Gangetic plain region. Okay. So, that point is extremely important to be kept while going for the site selection and all that. Okay. And there is no option, because we are sitting in an alluvial plains. Okay. So, we need to consider those parameters while coming up with the construction. Okay. So, I hope this lecture helped you a lot. Okay. And the last slide which I have is just to explain you that this is another data set which you can use to identify the major landforms. Okay. Because for identifying the precise active faults and all that, you need a very high resolution data, but on a regional scale you can pick up easily the folds, and I can quickly draw the ridge line here or the hinge line. Okay, which you can pick up from here, that this is then, and then the outer part of the fold you can quickly pick up like this. Okay. So, these are the datas which are available, and or you can buy from NRSC, which can help you in identifying different landforms. So, and this is another one very good example which has been given. Okay, that the house which was sitting close to the rupture, okay, that is the fault line, got damaged here, but the other house just escaped the damage. Okay. So, this is the another important part. Okay, fine. And this is from Taiwan during the Chichi earthquake 1999, magnitude was 7.7. There is another one from 2005 Muzaffarabad earthquake or Kashmir earthquake, where this is the fault scarp here. Okay. This is the fault scarp, and the fault runs somewhere over here. Okay, at the base here. Now, the houses and this fault scarp is a thrust fault scarp. Okay. So, this is your foot wall, and this is your hanging wall. So, hanging wall moved and the foot wall remained stationary. The house sitting here was safe, but what you see on the top of the scarp, okay, all this whitish block are the roof of those houses which were completely raised to ground. Okay, fine. So, this is what the difference you can identify. So, you cannot have much of construction on the active fault scarp. Okay, you need to be away from that, and then you need to understand that what is the lithology of that area and how far the houses which we are going to construct will withstand the ground shaking. Okay. So, ground shaking on the hanging wall close to the fault will be much higher, okay, as compared to the foot wall. I do not say that there will not be any ground acceleration, but of course, comparatively or you can say relatively less acceleration will be on the foot wall side. Okay. So, this is another example which we based on sort of a lesson which we learned from 2005 Muzaffarabad earthquake. Close up of that, all the houses sitting in the footwall were okay, nothing happened to those houses, but all the houses which were constructed on the top of the active fault scarp were raised to ground. Okay. Again, you can use different type of data to identify the landforms, and this is one of the data which we have taken. Again, this is Landsat data, which shows the area around the foothill zone of Dehradun and all. Okay. So, finally, I would say, is this your fault or not? And with that I will end this part of our lecture series, and then we will move to the next topic in coming lectures. Okay. Thank you so much.